So in this chapter, we are learning about something called thermodynamics. This has to do with the energy of the universe. And we start off by revisiting the topic of the first law of thermodynamics. So you learned about this law in Chem 1, and that might have been a while ago, so I'm just going to give you a quick refresher on this. So the law of conservation of energy has to do with the total energy in the universe. And basically the main idea is that it can't be created or destroyed. So as an example or idea, I have here some GIFs from The Simpsons. GIFs, I don't know. Some GIFs from The Simpsons, and it's this episode where Lisa, I think it's Lisa, she creates this little machine, and basically it's a perpetual motion machine that like keeps on generating energy without you having to put in any energy at all, which actually makes no sense at all. So that's why Homer's like, in this law we obey the laws of thermodynamics, because this is not possible based off of the laws of thermodynamics, especially because of the first law. We can't create it or destroy it. So anytime you have some sort of machine like this that has, an energy output, you have to have something inputting the energy. So you can't create that energy out of nowhere. So that's why he says that. And that's why it applies to this. So yeah, therefore we can't design a system that will produce energy without inputting it from somewhere. So here's just some more refreshers on some ideas and topics related to conservation of energy and the first law of thermodynamics that we learned about in Chem 1. So we learned about types of reactions, how we can classify them as either exothermic or endothermic. So exothermic is whenever you lose heat from your system to the surroundings. Now overall, the internal energy, something called the internal energy, is changing of this system. And the way that you lose energy or change the energy is through heat and work. Whether it's being lost or gained, it's always through heat and work. These are your two pathways. Internal energy is a state function. So it's independent of how it's done. You just look at the final and initial states. And overall, what can change it is the heat and work. So there is something called the heat tax. So for chemical and physical processes, the more steps you have, the more chances you have at losing heat somewhere. So for example, when you're heating something with electricity, you're first going to have to burn the fossil fuel, you're going to lose some heat there. Then you have to make steam, you're going to lose some heat there. Then you generate the electricity, you lose some heat. So the more steps you have, the more chances you have for losing heat, and overall this is called we term this the heat tax, versus whenever you just have one step, you'll just lose heat at one step, and then overall, you have like a higher efficiency of what you're putting in versus getting out. So that was some review about Chem 1 and what we learned, the extent of what we learned about thermodynamics back in Chem 1. Now we are going to learn about some more topics, and we're starting off with spontaneity. So will a reaction occur, quote unquote naturally at a given temperature and pressure without the exertion of any outside force? So will a reaction, let's say if you have the two reactants somehow together, will this reaction just happen on its own without you needing to put either some sort of energy into it? What you're actually asking, even if you didn't know this, is this reaction spontaneous? So spontaneity is it has to do with whether a reaction will occur like on its own. So a process that does occur naturally under a specific set of conditions, of course, right? We always have specificities in chemistry. We can't say like in general, but under a specific set of conditions is called a spontaneous process. A process that does not occur naturally under these conditions is called non-spontaneous. One thing I do want to point out early on right now is spontaneity has nothing to do with fast or slow. So just because something is spontaneous and will happen on its own doesn't mean it's going to happen right away. It may take a year, it may take seconds, it may take a billion years. So it has nothing to do with time. That's kinetics, okay? Thermodynamics and kinetics don't cross except in very specific places, which we have discussed a little bit about. But for this, it doesn't, just because something's spontaneous doesn't mean it's going to be fast or slow. A spontaneous process occurs naturally, without any outside forces, again. So an example is a mixture of hydrogen and oxygen. It'll react in the presence of a spark, and you'll end up getting some water. So in terms of whether spontaneous reactions are reversible, we actually have to think about what happens with energy. So any spontaneous process is actually irreversible because there is a net release of energy when it proceeds in that direction. So whatever happens to it, let's say for example you have a car, it's a spontaneous reaction for it to rust, for it to react with oxygen and then form like iron oxide or whatever other rust you're forming, because different metals, react differently. But anyway, this formation of iron oxide overall releases energy. So because of that, it only goes in that one direction. And I mean, think about it. When something rusts, it doesn't magically unrust by itself, right? So this going from, shiny metal, iron, whatever it is, to rusty, old, clunky car happens on its own. You've seen these things in your daily life. But the other way around does not happen, and it's because it's non-spontaneous. So a reversible process will proceed back and forth. This is whenever we have something at equilibrium, so we learned about this already. But for these spontaneous reactions, we only have them in one direction. And in order for something to go the other way around, it's going to be non-spontaneous. You're going to have to put some sort of energy into it in order for it to happen. So here we have some visuals of spontaneity. So first, something kind of easier for you to visualize. You having some sort of mass on a pulley and you're pulling the mass up, that would be non-spontaneous because you have to put some work into it, right? But it falling down is spontaneous. It just happens on its own. Another example is you have some sodium chloride. It is spontaneous for it, whenever you put it in water, for it to dissolve. It'll just dissolve into its ions on its own. You don't have to really do anything, just maybe stir it around a little bit. But in order to go the other way around, the ions to the solid, that would be non-spontaneous. So here's a graph depicting the idea of kinetics versus thermodynamics. So thermodynamics, we only look at initial and final states. And this has to do with spontaneity, whether it's going to happen on its own or not, right? And if it happens on its own, you'll get the reactants turn into the products by themselves. Kinetics has to do with speed. Kinetics has to do with how you actually got there. So if you remember what a state function is versus not a state function, this is not a state function versus thermodynamics is a state function because all you look at is the final minus the initial. Versus kinetics, you actually have to pay attention to how you got there, which is what affects the time. So to further illustrate how spontaneity doesn't have anything to do with kinetics, here we have an example which I think is very interesting. We have diamond, which is a carbon solid, and graphite, which is also a carbon solid. These are two allotropes to each other. I know this isn't on the slide, but that's what these are to each other, if you're wondering. They are the same exact element and the same exact state, except they're bonded to each other differently, so you get something called an allotrope. But overall, diamond turning into graphite is spontaneous. it happens on its own. So imagine you have a diamond ring and then one day you look at it and it turned into graphite. Well, this can actually happen. But the thing is, it's very slow. So in your lifetime, this wouldn't actually occur. It takes like billions and billions of years. But you don't have to worry about this happening. It will literally take so many years. But this is spontaneous. So if there was some way for us to stay alive for billions of years, we would see this happen over that time period. So overall, we said that spontaneous processes release energy, right? Which, if we go back to the definitions we've learned about previously, this would mean that it's exothermic. But there are some spontaneous processes that are endothermic. So how can these spontaneous processes that absorb energy have an overall net release of energy to make them spontaneous? So this actually has to do with something called entropy. So this is a new term that we are learning. Entropy has to do with randomness. So when a solid melts, for example, ice, think of ice, you're starting off with the molecules being kind of very rigid, stacked on each other. Think of them like that. Versus whenever they melt, they can move around. Remember, liquids have the ability to flow, and that has to do with the fact that the molecules are able to move around. So when a solid melts, the particles have more freedom of movement. More freedom of motion or movement increases the randomness. And when systems become more random, energy is released. Overall, this is called entropy. So when something melts from a solid to a liquid, you have increasing entropy. And the opposite is true. When something turns into a solid from a liquid, then you have decreasing entropy. Now, overall, if we look at this in the standpoint of whether it's endothermic or exothermic, remember that is delta H enthalpy. If we look at it in that lens, melting a solid is endothermic because it's required for you to heat it up, right? Think of ice cream. You have it in the cold and then you bring it outside of the freezer and it starts melting because it's hotter outside of the freezer. So overall, you're putting heat into it in order for it to melt. And the same thing with ice. Like if you put an ice on your hand, an ice cube on your hand, the palm of your hand, it's going to melt. And the heat is coming from your hand to the ice cube to melt it. So it's an endothermic process, but it'll happen on its own. And that has to do with the randomness, the fact that it's becoming more random and entropy is increasing. The universe likes entropy, basically. That's like a main idea you should gather from this. And something you can relate to it is how the universe is expanding. It's becoming more random. The further things get away from each other, the more they can move. It's becoming more random. That's increased entropy, and the universe favors this. So the factors that affect whether a reaction is spontaneous are two things, and we actually already discussed them. I briefly touched on the enthalpy, but I did go in depth about entropy. So the two factors are enthalpy change and entropy change. So those are the two things that determine whether a reaction is spontaneous. So enthalpy change is the overall change in heat. And there's a further definition about the internal energy and PV work, but overall just think of it right now like the change in heat related to the reaction. Entropy change is the difference in randomness of reactants compared to products. So these are the two things that affect spontaneity. So some more review on enthalpy, since now we have discussed how this is one of the factors that affects spontaneity. So delta H enthalpy change is generally measured in kilojoules per mole. When a reaction is exothermic, then that means that the bonds in the products are stronger than the bonds in the reactant. So this has to do with the fact that stronger bonds means more stable. The universe likes more stable things. So if the bonds are stronger in the reactants, it's going to release more energy, and it's going to be exothermic. And remember how overall spontaneity releases energy. So this helps that spontaneity out. So energy is released, delta H is negative. When a reaction is endothermic, the bonds of the products are weaker, so it's going to require a lot of energy to break those reactant bonds in order to form, those bonds in the products. So overall, you'll get an endothermic reaction. Energy is absorbed, delta H is positive. The enthalpy change is favorable for exothermic reactions, unfavorable for endothermic reactions. It's favorable for exothermic because you're overall releasing more energy, which contributes to spontaneity. So here we have some spontaneous processes, and we are going to discuss how the matter is being redistributed and how it's contributing to it being spontaneous. So first we have a solid subliming. Sublimation is whenever you're going from solid to gas directly without, with skipping the liquid phase. And whenever this happens, we are starting off with a solid which has a high density, and then we're going to a gas which has a low density. Whenever this happens, we are ending up with a greater volume, right? Because the gas takes up whatever volume it possibly can, versus a solid has a definite volume, definite shape. So this ends up having a greater dispersal of matter, so a greater redistribution of matter. So honestly here we're just kind of thinking about what's happening and kind of trying to visualize it. For B, when a gas condenses, we are going from a low density, so it's the opposite. We're going from a gas to a liquid, right? Not directly to a solid, but we're going from a low density to a higher density. So because of this, we have a not as great redistribution. We're actually doing the opposite. We're condensing it. I know that's not the best word, but we're going from a large volume to a smaller volume. And then finally, example C, we are dropping a food coloring into a glass of water, and it forms a solution with a uniform color. So we start off, clear, and then we drop the food coloring. It disperses. So this one's easier to, actually see because we can literally see the color. So what's actually happening here is diffusion. And here we have a higher redistribution of matter. It's dispersing everywhere into the liquid until it's uniform.